Okay, welcome all. Today we are going to discuss the topics. Draw the register structure of 8051 and explain it. In the yesterday's class, we have seen about the functional block diagram of 8051, and we have also learned about the function of each block with the explanation. Now moving on to the next topic, that is the register structure of 8051 has many, that is number of registers, but how they are arranged, how we can access them, how they will be utilized, whether they are bit addressable or byte addressable. So these all things we will learn in this topic. So register used to store the data temporarily, right? If we can remember from the digital electronics subject, that is generally flip flop will be used for memory. I mean, it is a single bit memory, and in case of registers, it is a group of flip flops. Group of flip flops. So depending on the number of flip flops, it will have the number of bits. Generally, it will be 8 bits or 16 bits, like that. It will have. So they will store the data temporarily. The data may be of opcodes, that is operational codes, or operands, or address of a memory location, or address of a peripheral. The 8051 has wide range of registers. These are classified as general purpose registers, special purpose registers, that is microcontroller related registers, special function registers, special purpose register, and special function registers, SFRs. We can simply call special function registers as SFRs. Now please draw this diagram, that is the registers. So what are the different types of registers we have, and the names of these different registers also. Please, everybody, please draw this diagram. I will give you 2 minutes. Okay, I hope everyone has drawn this tree diagram. Now, see, just look at the diagram. That is the register structure of 8051. In the top, we have, and it is classified into general purpose register, special purpose registers, and special function registers. In case of general purpose registers, we have A register accumulator, B register, and register banks. And if we can remember from the features of 8051 topic, that we have 4 register banks: bank 0, bank 1, bank 2, bank 3, and in each and every bank we have registers named from R0 to R7, that is 8 registers: R0, R1, R2, R3, and up to R7. So we have 4 register banks, an accumulator register, and B register as general purpose registers. And in case of special purpose registers, we have PC, SP, DPTR, and PSW. PC means program counter. SP means, what is SP? Special pointer. SP register. Sorry, stock pointer. It is stock pointer register. And DPTR means data pointer register. PSW means program status word. So from the name itself, we can see general purpose registers will be used in generally, but is for several applications, for several data processing, data fetching, and we can use it generally. That means any value can be fetched from these registers. But the special purpose registers are used for only specific application and specific purpose only. Program counter, from the name itself, we can see it will be used to count the number of instructions or count the number of machine cycles itself. So when we write the opcode, when we write the program, this PC will point to the next instruction which is going to be executed. will point to the next instruction which is going to be executed. That means it will make ready in the processor to execute the next instruction. So it will fetch the next, that way it will save the time. That means it will speed up the process. It will increase the speed of the microcontroller. Stock pointer, we have a stock here. It will point to the top of the stock pointer register. So upon adding this data onto the top of the stock, it will increase, and upon taking out, that is push, we can call it as pushing and popping of instructions. If you push the instruction or push the data onto the stock pointer, then the stock pointer will increase. And if you pop, that means if you take out the data from this stock pointer, it will be decremented by 1. So that is the stock pointer will do. It will point to the top of the stock. And DPTR, data pointer register, it is an external it will point to the external memories. If you want to fetch the data from the external memories, it is a 16-bit pointer. And PSW, program status word register, that means what is the status of this program, that means what are the status of the flags. We'll have the flags register, flags. So depending on those flags values, we can see what is the status of this program. And moving on to the next type of register, that is special function register, that is tmod, tcon, that is timer mod, timer control, I interrupt enable, and IP interrupt priority, scon serial communication, and pcon, sorry, I don't remember pcon, that is an sbuff serial buff register. Pcon means power control register. And P0 to P3, that is port 0 to port 3. We have 4 ports, right? Port 0 to port 3, port 0, port 1, port 2, port 3, which will have, each one will have 8 pins. Port 0.0 to port 0.7, port 1.0 to port 1.7, like that. We have 32 IO lines, 32 IO lines, input and output lines. So the general purpose register. Now we are moving on to the explanation of these registers. The 8051 has 34 general purpose registers. They are accumulator register, that is A, register B, and remaining 32 registers are arranged as a part of internal 128 byte RAM. All these registers are programmable registers. They can be used in the program, right? They can directly accessible in the program. We can write directly their names in the opcode program. So you no need to draw this diagram, but see, observe the diagram. That is, A register is from 0 to 7, that is, it is a 8-bit register. A register is a 8-bit register. And B is also a general purpose register. It is also a 8-bit register, but is 0 to 7. And we have 4 register banks, right? 4 register banks, that is bank 0, bank 1, bank 2, and up to bank 3. In every bank of registers, we have 8 registers, that is R0 to R7. And they are mentioned as 0, 1, 2, 3, 4. That is just the number. So we have similarly same registers R0 to R7 registers in the same bank 0, bank 1, bank 2, and bank 3 also. Now the general purpose registers in this functions. What will do the R0 to R7 registers? The lowest 32 bytes, that is address 00H to 1H of the on-chip RAM. On-chip RAM has 128 bytes, right? So 128 means, if we can convert that 128 into hexadecimal, and from the 00 to 1F, 1F in hexadecimal, how much it will be? F means 15 and 16. 16 plus 15, that is 30, 31, that is 0 to 31, that means 32 total, 32 register, 32 byte address. The lowest 32 byte address of the entire 128 bytes of RAM. So form the 4 banks. So there are 128 bytes of RAM in the 8051. the lowest 32 byte address, that is 00 to 1F of the on-chip RAM from the four banks. There are four register banks are numbered 0 to 3. Each bank is made up of 8 registers named R0 to R7. These are used to store data temporarily. Already we have discussed this point. RAM location from 00 to 07H are set aside for bank 0 and R0 to R7, where R0 is RAM location 00H. R1 is in RAM location we have 01H. See this side we have 0, 1, 2, 3, right? That is the address of this registers 00, 01, 02, 03, 04H, 05H, 06H, 07H, and 08, 09, 0A. Like that you can see. So the second bank of register R0 to R7 starts at RAM location 08H and goes to location 0FH. And third bank 10H, 10H to 17H, 102, 17, and fourth bank, that is bank 3, from 18H to 1FH are set aside for the fourth bank. Okay, the figure shows how the 32 bytes are allocated into four banks. Note that only one register bank can be accessed by 8051 at any time. So at any point of time, we can access only one register bank, either bank 0, bank 1, bank 2, bank 3. And by default, it will be bank 0. By default, unless and until we specify, it will access the bank 0 registers. The bits RS1 and RS0, that is program status word registers fourth pin, or you can call it as fifth pin, because we will see from 0, right? PSW point 0, point 1, point 2, point 3, and point 4, that is the fifth bit. And RS0, this PSW, it's not PWS, it is PSW point 3, that is the fourth bit of the program status word are used to select any one of these four register banks as follows. So we have four registers banks, right? Or bank 0, bank 1, bank 2, bank 3. So in order to select which bank, we need to have 2 bits, because 4, to select these 4 choices, we need 2 bits, so that we will have the combination as 0 0 0 1 1 0 and 1 1. So one combination will lead to selection of one bank. So like that, we have 2 bits, that is RS0 and RS1. These 2 bits are a part of the PSW register, program status word register, as we have already mentioned PSW in this special purpose register. And the last one, PSW, special purpose register. And how the selection will be made, because RS0 and RS1 are the 2 points, sorry, two bits used to select this banks. So bank selection will happen like that. 0 0 will lead to bank 0, and 0 1 is the selection of bank 1, and 1 0 will be the selection of bank 2, and 1 1 will be the selection of bank 3. The default bank, that is on reset, is bank 0 upon, because it has the starting address, right? 00 to 07. So by default it will select this bank 0. Now see the general purpose registers. This name of this general purpose register is accumulator. The most important register, most important general purpose register is accumulator, and most widely used in every instruction is accumulator register A. So it is a 8-bit register. It is used for all arithmetic and logical operation. So for all arithmetic and logical operation, we will use this register. The A register must be used as destination for all addition and subtraction operation, because after the addition, the result, right? The result will be there, and after the subtraction, so after every arithmetic operation, we will have the result. So where will that result will be stored? That means that will be stored automatically in the accumulator register. Though accumulator will have one operand during this operation, that let us say example sum of a comma b, right? Sum a comma b, in that instruction a will have one operand and b will have another operand. Upon summing, the result will be there, that is automatically will be stored in the accumulator itself. So the operand which is stored in the accumulator previously before the execution of the instruction will be replaced by this result. So that operand will be gone. So like that, for every operation, for every arithmetic and logical operation, the destination final result will be stored in this accumulator. For logical operation, this can be used as a source or a destination. There are some specific operations like clear, complement, rotate, and swapping. The data must be reside in a register only. So for such type of instruction, that is clear instruction, complement, rotate, and swapping type of instruction, the data must be stored in this a register only. Then only the instruction will be executed. Otherwise, it will show an error, syntax like error. And these are extra points. Do you know things? While multiplying, it holds one of the 8-bit operands, and after the execution of the multiplication instruction, it stores the lower byte of the result. Because when we multiply two 8-bit operands, we will get a result more than 8 bits, right? So then we will have lower bits, lower 8 bits, and that is lower byte we can call, and upper byte. So and we mentioned accumulator register as 8-bit only. First point, that is, it is a 8-bit register only. So the resultant will have the result after multiplying these two 8-bit operands will be more than 8 bits, that is lower byte and upper byte. So in that case the lower byte will be stored in this accumulator and the higher byte will be in the other register. While dividing also, it holds an 8-bit dividend, and after the execution of division instruction, the quotient is stored in a register. So in this type of instruction, in the second chapter or third chapter, we will have these instructions, and we'll particularly learn with an example. With even the examples, we can learn, and we can see in the lab also the video writing the program, and we can see the results in the registers. Okay, no need to worry about it now. But this is, you can understand that most of the operations, most of the arithmetic and logical operations, we will use the accumulator register only. Now the next register, next general purpose register is B register. It is an 8-bit register. It is used for multiplication and division along with the accumulator. In case of this multiplication and division, we will use, we need two operands, right? For multiplication, it need to be, for division also it may be, such type of operations we will need two registers. You can say, sir, for summing also, divide and subtraction also, we will need two operands, right? In that case, the summing and subtraction operands, so we can use this B register, or without the B register also we can directly write those operands in the instruction itself. In the instruction itself, we can write directly the operands. No need to use the B register compulsorily. Okay. So while multiplying, it holds one of the 8-bit operands, and after the execution, the multiple instruction, it stores the higher byte. So in the case of accumulator, it will store the lower byte, right? But in the case of B register, it will store the higher byte. So if A into B, the resultant is greater than 8 bits, that is, it will have higher byte and lower byte. The lower byte will be stored in the A register, and the higher byte will be stored in the B register. So while dividing, it holds a 8-bit divisor, and after the execution of the division instruction, the remainder is stored in the B register. The remainder. So after the division, we will have the remainder and the quotient, right? So the remainder is stored in the B register, and the quotient is stored in this accumulator register. So we have seen all these general purpose registers, right? A register, B register, and register banks. In the register banks, we have R0 to R7. So these are general purpose. They will be used in this instruction, any type of instruction, right? So they are all 8-bit registers. Now the special purpose registers. The microcontroller contains 4 special purpose registers: program counter PC, stock pointer SP, data pointer DPTR, and program status word. In the SPR functions, first one, see the PC, that is program counters. Yes, you should learn each and every register, what it will do, how it will be used, what its function, how it can be accessed, what happens when it is not accessed, or what operations we can do on that particular registers, what operation we cannot do, right? How to write the instruction using this registers. Yes, everything one must learn before we are moving on to the coding, writing the program. So PC means it's a program counter, it is a 16-bit registers. Till now we have seen in the general purpose we have A register, B register and register banks from R0 to R7 in the 4 banks, but all of them are 8-bit registers. In the case of PC it is a 16-bit register. It is used to hold the address of the next instruction to be fetched. You may underline that line exactly, because it will hold the address of the next instruction to be fetched. The PC is automatically incremented to point the next instruction in the program sequence after execution of the current instruction. PC is automatically incremented, so nobody is going to tell that PC that you should go to that place or you should bring the address of the next instruction, but it will automatically, that is its function. It is designed for that purpose. So it is a design part. We no need to write every instruction after that we should write point it to the next address. So we no need to mention in the coding this PC. It will automatically, it will be going to be implemented. That is, it will point out to the next instruction to be fetched. PC is the only register that does not have an internal RAM address. See, this is important. In the PC, it is the only register that does not have an internal RAM address. So it will not have any address. Next is the stock pointer. A group of memory locations in RAM. In RAM itself, in the internal RAM itself, we have a section. RAM is 128 bytes, right? So we have 002 7F, 002 7FH. In that we have already taken 002 1F to the register banks. So there will be some other portion. After 202 7F, we will have some portion will be dedicated to this stock pointer, the stock section. So a group of memory locations in RAM is referred to as stock. The stack can store data as well as address during execution of the program. The stack, the memory location, can store both the data as well as address during the execution of the program. The 8-bit stack pointer, the stack pointer is a 8-bit, because in the RAM we have 128 bytes, that is each and every address will have a single byte. So that means a group of 8 bits. So it is also 8-bit register. It is used by the 8051 to access the stack. It holds the address of the top of the stack. It holds the address of the top of the stack. So the stock is a group of memory locations. In the stock pointer SP register will point out in the top of the stack section. That is, after filling, after the data is entered into this memory locations, let us say we have used 5 memory locations, then the stock pointer will be pointed to the 5th register of the 5th memory address. If you take out one value out of that particular stack, then the stack pointer will be reduced by 1, that is, it will be pointing to the 4th register address. So like that will happen. After the reset operation, the stack pointer is initialized to 07H, causing the stack to begin at 08H. 0708, because in the register banks we have 00207 for the bank 0. By default, upon reset, the register bank will be selected, that is the bank 0 itself selected. So 00207 is occupied. 00207 is occupied. So stock to begin with 08 upon reset. When the data is stored on the stack, the SP value is incremented by 1. The data is stored on the stack, the stack pointer value is incremented by 1. Similarly, while retrieving the data from the stack, the SP value is decremented by 1. So SP plus 1 or SP minus 1. The data is pushed onto the stack using the instruction push instruction. And the data is retrieved using the instruction pop. So these are the instructions which are specifically designed for the stack. That is push instruction to store the value onto the top of the stack. The pop instruction to retrieve the value from the top of the stack. And DPTR, data pointer register. DPTR register is made up of two 8-bit registers. It is made up of two 8-bit registers. You can say it is a 16-bit register that is divided into two registers. That is named DPH, data pointer high, and DPL, data pointer low. In the DPH we have the address as 83H. In the DPL we have address of 82H. It is a 16-bit address, so DPL and DPLH will have 8-bit. Its function is to hold a 16-bit address. The data pointer is used for addressing the off-chip data, that is external data, and code with the MOVX and MOVC commands respectively. So these are the mnemonics we will use during the writing of code. We have move instruction, MOV. English word is MOVE, but in the mnemonics we don't use the exact English letters. We will use mnemonics. Mnemonics means the English-like words, but specifically designed to write the code language. They may be spelling wise it may be wrong, but they will be for the code. So similar, that is the example. MOV, move, to transfer data from one position to another, so one register to another register. So we will use MOV for internal transfer of data, internal register wise, register to memory or memory register, or register to register also. But in the case of DPTR, it is 16-bit register which will pointed to the off-chip data. So we will use special mnemonics, that is MOVX and MOVC. This part also we can see in the coding section, that is in the second chapter or third chapter. Now next register, that is PSW, program status word. It is a 8-bit register. It consists of 4 flags and 2 bits for bank selection of internal RAM. In the bank selection section, as earlier slide we have seen, there is a RS1 and RS0, two bits used for the bank selection, which are from the PSW register, right? PSW band 4 and PSW band 3. So these are the 2 bits we have in the PSW, and along with these 2 we have another registers, that is 4 flags and these 2 bits. So it is a 8-bit register. 4 flags will be there, 2 registers anyway. So 6 are over, but one is reserved for the future purpose, that is dash symbol. You can see that is D1 bit is reserved for future purpose, and we have flags, parity flag, overflow, user flag register. So this is also reserved user flag. We can design this user flag while writing the code. We can use it as we like, as a flag, very option. But this parity flag, carry flag, and auxiliary carry flag will be specified. They will be used for specific application, specific condition only. They will be set and reset. Okay, so now we are going to look at the PSW register, program status bar. This is important register. This is one of the important register in case of 8051 controller. So in this PSW register, Program status word or simply PSW register is one of the most important SFRs. It is a 8-bit register. It consists of 4 conditional flags that set or reset automatically to the outcomes of mathematical operations. There is carry flag CY, auxiliary carry flag AC, overflow flag OV, and parity flag P. Two register bank selection bits, that is RS1 and RS0. A general purpose flag F0, F0. Figure shows the bit pattern of the program status word. Yes, you must draw this bit register. So you must draw this register along with those flags, name of the flags also. We have D0, D1 up to D7, that is 8 bits, 8 data bits you can say. And the first one D0 is a P, that is a parity flag. The second one is a dash, that is nothing is there, that is reserved for future purpose. That means during the design process they may left this bit vacant so that in the future some flags may be utilized, some flags may be discovered, so we can use it in the program. And the next is OV, that means overflow flag. RS0 register bank selection bit 0, RS1 register bank selection bit 1, F0 that is user flag register, and AC is for auxiliary carry flag, and CY is for carry flag. And the conditional flags, we have seen that is 4 conditional flags are there. So first one is carry flag. Carry flag is set if there is a carry from bit 7. Bit 7, that is we have bit 8 bits, right? 0 to 7 bits. If there is a carry from 7th bit during this additions, right, it is used in arithmetic, jump, rotates, and boolean instructions. So during the mathematical operations we will have carry from the last bit, right? So if there is a carry from the 7th bit, then this carry flag will be set, that means it will become 1, otherwise it will be 0, reset. If there is no carry from bit 7, then it will be, the carry flag will be reset, that would mean the carry flag bit CY bit will be 0, and this carry flag can be used in the arithmetic, jump, rotate, and boolean instructions. We can see all these instructions in the second lesson. Then the next flag is auxiliary carry flag. Auxiliary carry flag is set when there is a carry out of third bit. Third bit meaning, because the 1 byte we can divide it into 2 nibbles, right? 1 byte is divided into 2 nibbles, lower nibble and higher nibble. In the lower nibble we have bit 0 to bit 3, and in the higher nibble we have bit 4 to bit 7. So during some mathematical operations, that is addition or subtraction, there is a chance, there is a condition when there is a carry out of this third bit, then the carry flag will be set, otherwise the carry flag will become auxiliary carry flag will be reset. This is used for BCD operations, binary coded decimal operations only. Binary code, in the binary coded decimal operation we should add 6, right, to the output if it exceeds 9, that is if there is a 10, 11, 12 such type of bits come in the result, then we should add 6 plus 6 to this result, then only it will be represented in BCD format. So such type of operations will be detected by this auxiliary carry flag. Next is overflow flag. The overflow flag is set if there is a carry from bit 7, but not from bit 6, but not from the bit 6. There is a carry from bit 6 but not from bit 7, otherwise it is clear. See, the overflow condition will occur when there is a carry from bit 7 and but not from the bit 6. And if there is a carry from bit 6 and not from bit 7, then it is clear. This condition we can easily understand when there is a program we write, and we can see it in the example also. Next is the parity flag. The parity flag is set if the accumulator contains an odd number of ones. Parity flag will be set if the accumulator contains. So where we have to see for the parity flag condition, that is in the accumulator only we will see the data, right? The entire arithmetic operation or mathematical operations results will be stored in the accumulator. So in the accumulator data, if there is odd number of ones are there, so accumulator will have 8 bits, right? So in those 8 bits, if there is number of ones is odd, then it will be set, parity flag will become 1. If not number of ones are odd, then there will be number of ones will become even, then that flag register is reset. It is mainly used during data transmit and receive via serial communication. Via serial communication. Next is register bank selection bits RS1 and RS0. These two bits are used to select one of the four register banks of RAM. Below table shows the address ranges of four register banks along with RS1 and RS0 bits. We have already seen this register selection bank, that is RS1 and RS0 for the bank, and the address range also we have known that 00207 0820. Next we can move on to the next user selection, that is F0 general purpose flag. F0 flag, F0 is available to user as a general purpose flag. This flag can be set or cleared by software, or its status can be observed by software. The user can define its role. We can define its role. Users, we actually you people can also define its role, how it will function, you can also define. And the note section we have PSW is a bit addressable register. This is important. PSW is a bit addressable register. Till now we have seen accumulator register, B register, and registers R0 to R7. Those are not bit addressable. Unless until we mention that is bit addressable, it will be byte addressable only. Unless until we mention particular register as a bit addressable, they all will be byte addressable only. Each of the PSW bits is referred as PSW.x, is PSW.0, .1, .2, up to .7. Thus PSW0 is the LSB, which is a parity flag. PSW0 is the LSB, which is a parity flag, and the MSB PSW.7 is the carry flag. Here we can see from the diagram, that is PSW.0 is the LSB, D0 is a P flag, parity flag. The PSW.7, that is the end bit, it is a CY, that is a carry flag. So with this we have completed today's topics. Just quickly revision because we have only 5 to 6 minutes. So every word is new word to you. That means whoever listening to this class, that is whoever not learned about the microcontroller, the topic of microcontroller or any of the particular microcontroller, either 8051 or something else microcontroller. So you should learn step by step and clearly, and it may take more time in the initial part, but when we enter into the second chapter, third chapter, we can quickly move on to the next other topics by explaining each and every topic quickly. So in the today's lesson, let's revise. This is yesterday's section, right? The functional block diagram. Topic of functional block. I hope everyone has done this functional block diagram in the homework part, because in the yesterday's class I don't give any time to draw this diagram, but one must compulsorily draw this diagram by mentioning all those particular blocks, and you should remember those blocks. The particular 8051 IC may be of size of almost 5 to 6 centimeters only. 8051 IC in the practical world it will be around 5 to 6 centimeters, but in that area only we will have these many blocks. These many blocks are interconnected. If you see the internal diagram, the construction, then you will wonder how the technology improved. It is happened in the 1980s itself, not today's world. In the 1980s, we don't have much of this technology, right? So, so this is yesterday's class. Function block diagram, different parts, how they will do. And today we have seen the register structure, right? Register structure. What registers, what type of registers we will have, 8051 is having, and what are their purpose, how they will be accessed, what is the address of the registers, what is the purpose, how they will function. So those topics we have covered today. In the general purpose section we have accumulator and B register banks, 4 register banks. Special purpose registers we have 4 registers, that is program counter. Again and again you should learn and read these registers again and again, then only you can remember easily. Right? Program counter and stack pointer, data pointer, and PSW program status word register. And the special function registers we have tmod, tcon, IEIP, scon, pcon, sdoc, p. So we have seen only these 2 sections, right? General purpose register and special purpose register. We will see these special function registers in tomorrow's class. In the general purpose we have this 34 general purpose registers. This can be direct question in your competitive exams or in the interview sections. What are the number of general purpose registers in case of 805? They can mention 34, 32, 30, 24, and they can ask the address of this register bank, bank 0. What is the address range of this bank 0? Address range of bank 3. Next, whether accumulator is 8-bit register, 16-bit register, that is going to be a simple question. Next, so such type of questions you can expect. What is the capacity of internal RAM? What is the size of the internal RAM of 8051? So number of questions, thousands of questions you can expect, and you can even practice this type of questions in the websites, that is I have mentioned in the sandfoundry.com, that you will have number of MCQs you can practice, and in the other websites also you can find number of questions also. And keep your functions R0 to R7, how they are arranged in the internal RAM, what is the address range, right? Particular 32 bytes of internal 4 banks, and the RS0 and RS1 register selection bank bits. In the earlier part you can remember these things easily, but as we move on to the next chapters it will be hectic. That means the syllabus will be increased and you have to remember a lot of the functions, then you may forget these basics here. RS0, RS1, where we have seen this, what is their purpose. Okay, so one must revise and revisit, please study these topics again and again unless until you are familiar with this registers and each and every point you have to be remember. And default bank upon default, this can be also question, default bank on default and recent, what is the bank selection, that is bank 0 will be selected. The accumulator register, most important register, 8-bit register, use it for all arithmetic and numerical operations. Multiplying we have stored the lower byte, in the dividing it will store the quotient, the B register, multiplication and division. Multiplying it will store the higher byte, and dividing it will store the remainder. Special purpose program counter, stack pointer. Program counter will point out the next instruction address to be fetched. There is no on-chip, what it is, the PC is only register that does not have an internal on-chip RAM address. This can also be questioned in the bio also, in the lab bio, in the exam, final exams bio also. You can expect many number of questions. It's just not for the question and answer type of study. One must remember this. This is a simple 8051. Actually, this is a simple microcontroller. This is the basic microcontroller one must learn. There will be advanced microcontrollers in today's world. This one is the basic, because in the diploma level you will be learning the basic microcontroller. Then in your graduation level or PG level, you are going to learn different microcontrollers. So then you will remember this. You will compare this 8051 with the other microcontrollers. Then you will assess what is the improvements in coming years. That is 1980 they have made this 8051. So in the coming years, 1990s and 2000s, what are the advancements, what are the extra features, right? What is the capacity, whether it will increase or decrease. Different types of options will also be there. Different types of blocks, new blocks will be introduced in the functional block diagram. So PSW register, so everything, every point is important. There is nothing we can leave in this particular chapter or particular subject also. So thank you one and all. So with this I am closing today's lecture.